Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to introduce you to a concept called electric flux. So what I want you to imagine here, over on the right, I have described an electric field. Imagine we have an electric field of magnitude, we'll just call it E. This could be 10 Newton per Coulomb, 50 Newton per Coulomb, a billion Newton per Coulomb, it doesn't matter. Points in the plus I direction. So for the purpose of this example, we're going to be imagining a uniform electric field. Now, if the field is uniform, that means I can represent it with electric field vectors like I've already drawn. Right, so I drew a bunch of them here. These vectors are drawn to roughly equal length, and they're equally spaced, indicating a uniform electric field. Now, remember, the other way to imagine electric fields are to draw what are called electric field lines. So we can imagine, a bunch of field lines that point left to right, again, equally spaced because of the uniform electric field. It's not important that they line up right on the vectors. All right, so it's important to realize that these field lines, I've drawn, half a dozen or so of these field lines, but you have to imagine this is three-dimensional. There's more field lines along the z-axis. They go back into the page. You have to imagine a bunch of these field lines. All right, now, over here now, we've got this little hula hoop type of thing. And I'm not going to keep drawing them right now, but if I did, some of these lines are going through the hula hoop. And the number of lines that go through that hula hoop is described by a quantity called electric flux. Now, I'm going to talk a little bit about, how flux is calculated. So electric flux, okay, this is the Greek letter phi, typically used to represent flux, right, is equal to field strength, the electric field strength, times area. In this example, the area that we would be using is the surface area here, the area of this closed surface. Now, the reason the flux depends on the electric field, well, the stronger the field, the more field lines you would draw, and hence more of them would go through this area. Right? The reason why it would depend on area, well, if I could somehow make this larger, and my little thing here is practically magic, I think I can do that. If I were to make the area larger in some way, shape, or form, more field lines would go through it. Now less field lines go through it. More field lines would go through it. Less field lines go through it. So the number of field lines, and hence the electric flux, depends not only on the field strength, but also the area. And there's another thing it depends on as well that I can demonstrate pretty well here too. Also, if I rotate this, if I take this hula hoop and I rotate it maybe something like this, if I rotate it all the way so that basically it lies in the XZ plane here, none of the field lines would be going through my hoop anymore. So somehow orientation is also a factor. So I'm going to go ahead and, oops, there's some sort of problem, huh? I'll get rid of that. Oops. Go away. Let's see here. What do I click on to get rid of this? There's a problem with the website security. I'm not using website. Well, let me get back to my flux calculation. We're just going to pretend that isn't there. All right, so electric flux depends not only on the electric field, but also the area of the surface you're looking at, and it also depends on orientation. So I'm going to go ahead and put this thing in kind of a random orientation. All right. Now, I'm also going to draw an electric field vector at this point. So if I were to draw an electric field vector, I'm just going to draw one, right? Oops, I'm going to draw that in black like the other ones. Draw one electric field vector right here. Now, when we say that flux is field strength times area, we can't just take this electric field vector. We have to think of this electric field vector right now in terms of components. I'm going to go ahead and draw these in blue. I could break this electric field vector into a pair of components, one that's this way and one that's this way. This component is the component that is perpendicular to the area. This component is parallel to the area. When we're doing flux calculations, we need the component that is perpendicular to the area. Now, in this triangle right here, this is a right triangle, may not look like it, but use your imagination here. The hypotenuse is E, the electric field strength. The component, the perpendicular component, is adjacent to this angle theta right here. And therefore, E perpendicular is equal to the hypotenuse, which is the electric field strength, times the cosine of the angle theta. So another way we can express the flux is E cosine theta. That's the component of the electric field that's perpendicular to the area, right? And then times the area, or when we look in our textbook, this will probably say something like this, EA cosine theta. And then the cosine theta part takes into account the orientation of the area. Now, when you're dealing with any of these, with angles, you always have to be consistent with how we talk about angles. So, what I'm going to do is I'm going to define a new vector here that's going to have just a direction. So whatever my area is, this way is perpendicular to the area. Another way to say perpendicular is normal. I'm going to go ahead and draw this in green. So I'm going to draw a vector perpendicular to the area that's normal, and I'm just going to make it a unit vector. So n hat here represents a unit vector perpendicular to the area. So when we're doing the flux calculations, we take E cosine theta. What that gives us is it gives us the electric field component that's perpendicular to the area, but that component is parallel to the normal, this normal vector. So I'm going to go ahead and in future videos talk a little bit more about the normal and why we're defining it. For right now, I'm just going to say this. To calculate electric flux, it's EA cosine theta, so it has units of Newton per Coulomb meter squared. When you calculate it, the theta is between the electric field vector and the normal to the area. And what it measures is it measures the number of field lines going through any given area. I think that's going to be enough for this example. I'm going to go ahead and just stop this now and make some more. Everybody have a great day.